from the last point. Okay, so first of all, anybody have any homework questions? Didn't we just do that one?
No, that's the one that I talked to you about yesterday.
It's impossible? Okay, so we're doing mechanical vibrations. We've talked about spring mass systems. Today we're going to talk about torsion springs and pendulums. And then the last thing, we won't do this today, but we'll talk about force vibrations. When is it? It's just the final, yeah. Friday at 8 a.m. Yeah, I seem to get a lot of 8 a.m.s. That is terrible.
Throw the curve off.
Yeah. I'm not going to stay the whole 3 hours. I'll be gone at 10. But if you come at 8:30, that'd be fine. I'll stay till 10. That's your business. I'm not planning to do any testing of any kind, well, except the actual testing.
So is force vibration going to take up like the rest of the semester?
Yeah, we don't have too much time, but maybe we'll have time to. I've sort of been right. Yeah. Well, we only have. Well, yeah, 2 weeks. That's right. You're right. 2 weeks. No, that will not take the whole time, and I've been sort of kicking around in my head what to do. Oh, just give you the final before? I mean, well, I can make arrangements with people one-on-one if you want to take it early or whatever, and you have you need to have some kind of reason, so think of a reason. But
my squirrel died.
Yeah, he doesn't anymore.
No.
I
do have a bird friend. He's fucking pecking holes in the side of my apartment.
That's not a good friend.
No,
But so for what we would do for the rest of the semester, yeah, I've been sort of thinking about that. We didn't talk about kinetic energy of rigid bodies at all, or conservation of energy. We could just talk briefly about that. We could do a review that would, do some combined type problems, that would bring a few things together that might help solidify some stuff. So, yeah, I think you're right that this. Thank you. This will not take the whole rest of the time. But yeah, or we have right.
How about we do like trivia games, like
that I will never do in my whole life. Yeah, no, I. No, that's one thing. I know I just said you can never predict the future perfectly, but I will never play a dynamics trivia game in my class. Okay. It's more likely that I would have one of those parties where we set out, like, where we all make like boxes for each other to give each other Valentines and have like pop and candy. That's more likely than, it's not very likely, but it's more likely than playing a dynamics Jeopardy. Okay.
It was your idea, of course it is.
Yeah, I mean, for some people it's a great idea. For me, it's not a great idea, but you know, I don't know why it is so unappealing to me, but it's about as unappealing a thought as any dynamics related. Yeah, I understand what you're talking about, but no, we won't do that. Okay, so now we're talking about uh, torsion springs, and it works about the same as the spring mass system. You know, so you have some body, it doesn't matter what the shape is. And that's true. It does.
From a spring.
Okay, so you have, so that's a torsion spring connected to this thing. And let's call that point A. That's the point that the spring's connected to. Really what it is the point about which this body rotates. And the torsion spring works like this. It applies a couple that's equal to the negative spring constant, and that's the Greek letter kappa. You know, like with a linear spring, it's k, so this is the Greek letter for k, times the angular displacement. This is just the spring constant. You know, it's a torsion spring constant. This is the couple applied by the torsion spring. And this is the angular displacement. We're only going to do these problems in 2D, so we don't have to worry about any weird right-hand rule stuff. That's just positive is counterclockwise and negative is clockwise. And so if you draw a free body diagram like this, okay, so free body diagram of the body. There's the point A, and we have a couple applied by the spring. So I'll just write that as negative k theta. There are no other moments. I guess you could have the weight, but you could have the weight. Let's assume that this is also we'll assume that that about point is also the center of mass of the body. You would have, so if you didn't, I guess it would be sort of analogous the way you'd go through it to the derivation of the vibration of a spring mass system that's hanging vertically. You'd have this extra constant force that's applied by gravity that would apply another, well, that moment would depend a little bit on the, I don't know. Maybe we can do a problem like that later. Let's not do it today. Okay, so, and then you have this mg acting down. That's not going to come into the problem. And so the reason that I put that about point, that rotation point at the center of mass, is so this weight force wouldn't come into rotational Newton's second law. I don't know. So we have that the only moment about this is negative kappa times theta, and that's equal to the moment of inertia about A times the angular acceleration. And so you can rearrange this as IA alpha plus kappa theta is equal to 0. And since this problem is in the plane, you can rewrite this as I sub A times theta double dot plus kappa over IA times theta is equal to 0. I guess I did 2 steps here, so that's what it comes out to be. And this is the governing differential equation. Ordinary differential equation. And the general solution then you can see that that has the same form as the general governing ordinary differential equation for any unforced mechanical vibration problem. The general solution comes out to be that theta as a function of time is equal to the amplitude times the sine of the quantity square root of kappa over moment of inertia times t plus the phase angle. And so we get an oscillatory motion where now our dependent variable is that angular position theta. Any questions about that? Okay, so let's use this in a problem. So let's say that we have a disk rotating around this point A at its center of mass. Mass is 0.4 kilograms, and the radius is 0.1 meters. And the question is, what constant kappa would a torsion spring need to have so that the frequency of this thing is 0.5 seconds? The frequency is 0.5 hertz. by the way, this is like a very very simple form of the way the timing mechanism in an old-fashioned watch, pocket watch or wristwatch works. You have a torsion spring attached to a disc or a ring, and the moment of inertia of the ring and the strength of the torsion spring are such that this thing oscillates, say 4 times a second or something that you can use to measure increments of 1 second. And then every time it oscillates, it moves the hands. Okay, well, the moment of inertia of this disk about A is equal to the mass times the radius squared. And so that is 4 times 10 to the negative third kilogram meter squared. Our governing equation says theta double dot plus kappa over 4 times 10 to the minus third times theta is equal to 0. You could rewrite that as theta double dot plus 0.25 kappa times 10 to the third theta is equal to 0. And so the natural frequency, omega sub n, is equal to the square root of 0.25 times 10 to the third times the square root of kappa. Can someone tell me what that number is? Fifteen point eight one times square root of kappa. The frequency is 1 over 2 pi times the natural frequency, so that's 1 over 2 pi times 15.81 times square root of kappa, and that has to be equal to 0.5. So now we're solving for kappa. Those cancel. We get that square root of kappa is equal to pi over 15.81. Square both sides. And so what do you get for kappa? Two-thirds, right, Peter? 0.624. And then the units, well, we know that it's based on the equation, this relationship. We know that kappa is equal to Newton meters over radians. So this is just you can think of this as Newton meters per radian. Oh.
The whole thing, they did 0.039.
Yeah, square the whole thing. Yeah, so we're trying to find the strength of that spring that we need to get some prescribed frequency, if you're using that frequency for something. Okay, any questions about that? Yep.
So that's a productive day.
Yeah, but we're not even done yet. For most people, that would be a productive day.
There's a country that only 4 days a week, like 30 hours.
Yeah.
We should be more Finnish. Hey, we should finish.
Yeah.
Finish.
Okay, so next topic, pendulums. So we'll do this as, yeah, it's probably pendula, isn't it? I'm not saying that though. Okay, so I'm going to do it for a massless cable with a length L. And this is the angle theta that we're going to be dealing with. And this has a mass M. And we want to figure out the governing ordinary differential equation. And the general solution to that. Okay, so a free body diagram of the mass. And actually, what? Yeah. Let's actually think of this as being a rigid body that's the mass in the cable. So our free body diagram is, our free body is something like this. Okay. Cable isn't really rigid, but it acts like a rigid body in this motion. And so the loads, there's some contact force here that we don't know, and it's not going to come into our calculation. And then there's a weight, mg, and since the cable is weightless, that just acts at the center of mass of the mass at the end. Well, we'll do a problem sort of like that, but we just have to deal with, so we're going to use rotational Newton's second law. And so we're going to have to come up with a mass moment of inertia of this thing. So you just use the mass moment of inertia of whatever is oscillating. Okay, so what's the mass moment of inertia of this thing? And let's say, well, this is the about point. So let's do our rotational Newton's second law about this point A. Well, remember the definition of the mass moment of inertia is the integral over the entire mass of rho squared dm. So we're going to break up the body into masses at all these different locations, find the rho squared at each one of those, and then add them all up in a Riemann sum. This only has a mass at a single location. So in our case, this is just equal to L squared m. Yeah, or you can also think of it as the thing itself doesn't, since it's acting at a single point, we're treating this like it doesn't have any mass moment of inertia about its own center of mass. And then this is the parallel axis theorem term. Yeah, yeah, we're treating this like a particle. Oh, yeah. Mm-hmm. Yeah, finally. Yeah, so now the rotational Newton's second law about A. We have the moment produced by the weight. And break this up into a right triangle. This distance is negative because it's going to cause a clockwise rotation. Mg times L sine theta. L sine theta is the moment arm. No, all I want right here is the moment arm. So get the mg out of it. That's what's going to go into our equation. So the moment is negative mg. Get the negative out. Sorry about that. That's going to screw up your notebooks. So negative mg times L sine theta is equal to the mass moment of inertia, so ml squared, times the angular acceleration of this body. Clockwise, that's right. And rearrange this and you get ml squared alpha plus mgl sine theta is equal to 0. And you can divide everything by m, divide everything by one of these l's. And you get this governing equation. Well, I guess I'm not there yet. So we got alpha plus g over L sine theta equals 0. And then that alpha is equal to theta double dot. Yeah, I divided that out. So now it's over here. And so the final form is theta double dot plus g over L sine theta is equal to 0. Okay, so this is the general governing equation for a pendulum. But that is not the form that we've seen up until this point. Yeah, and then I divided both sides by L. And
No, but there's only one L on the sine theta side. So if you're pulling it from the other side, then it's, oh yeah, never mind.
Okay.
Yeah.
So this is uglier, and so we have to restrict this to come up with the form that we're used to. If you restrict this to small angles, then if you're dealing with small angles, in radians, the sine of the angle is roughly equal to the angle itself. And that gives the simpler form of the governing equation. But this only applies for small angles. So if you have a pendulum that's doing this big loop, this is not correct. So it's simpler governing equation. But is this trivia? Oh, I thought is this going to be on the trivia game that we're not going to play? Yeah, it's prettier. I know. What if that ends up being my favorite activity? Like the cornerstone of my teaching. Yeah. I'm not ever doing that. I'll retire. Yeah. No. Wrong. So the simpler governing equation, and this is for small, remember, this only applies for small theta. This is the one that we're going to use, but you need to know that that's only for small theta. As theta double dot plus G over L theta is equal to 0. Okay, and that one has the look that we're used to. Well, it just depends what kind of precision you need. But you know, if you want to see how close it is, just punch a couple angles in radians in your calculator and see what kind of error you get. You know, what kind of percentage error you get, and that'll tell you. What does it do to make it harder to solve this? Well, it's kind of hard to interpret what that physically does. I mean, we could do a numerical solution for that, but coming up with a solution for that, you know, nothing jumps to mind for how to come up with an explicit solution for that. So that's all. So in our perspective, all it does is make it hard to come up with a closed form solution for that differential equation. This we've already solved in multiple cases, you know, so that's what we like to see. And that's the only reason that we're making this restriction. Numerically, it's really easy to solve that. You know, like you can write a spreadsheet in Excel that showed you what that solution looks like. It just wouldn't be quite sinusoidal. It would still oscillate. It just wouldn't, and it would be roughly approximated by a sinusoidal function, just not completely. And how much it deviated from a sinusoidal function would depend on how far you pulled it before you let it start swinging. If you only pulled it 5 degrees, it would look exactly sinusoidal. You know, if you pulled it 40 degrees and let it go, it would deviate. Mm-hmm. Yeah. That's right. Yep. That's right. And that external force, I guess, I'd imagine that that's what, if you did this oscillation about something other than, I'm thinking of the torsion spring. But I think it's sort of the same thing as if you did the torsion spring thing, not about the center of mass. Okay, so the general solution for this is theta of t is equal to a times the sine of the quantity square root of g over L times t plus p. And like all the other cases, to find those constants, you need to plug in the boundary conditions that you have. Yeah, that's right. And notice that the mass doesn't come into this, although it sort of creeps in. It sort of gets in there in a sneaky way because this thing that you come up with only applies for a mass that's much bigger than the mass of the cable. If that mass gets smaller and starts to approach the mass of the cable, then you wouldn't be able to treat it as all the mass concentrated at one spot. What is phi? Well, phi that's the phase angle, which says, so that phi comes from the boundary conditions. And so what that's saying is the solution looks like this, and the boundary conditions tell you where on this your t equals 0 is. So if you pull it into negative theta and release it from rest, then there's your t equals 0. If you started at theta equals 0, but with a velocity, then here's your t equals 0. It just tells you where along that curve you start. It's an offset horizontally. And that's what a phase angle always is. That's what a phasor pedal for your electric guitar does, is shift the shifts the incoming sine waves so that they're hitting at different parts of their waves.
Was closer to the mass of the thing swinging on the pendulum, that's where you get like slack, and that would probably throw off.
No, it would still work. And actually, so what I want to do is an example problem where now instead of a mass on a weightless cable, we just have a beam, like a log or whatever, doing this, and do the same calculation. Okay, so now let's say that the system, okay, so swinging too high, yeah. Why does that happen? Yeah, I totally know what you mean. I'm not totally sure why that happens, but that has to do with the big angles, not the mass of the not the mass of the chain, I would think. Oh yeah, that does sound right. Yep. Yes. So gravity is fighting to keep the chain tight when you're close to when the chain's close to vertical, but as it gets closer to horizontal, gravity is not pulling the chain tight anymore. So something like that, yeah. Then the what? The Pinewood Derby? No, that was the most interesting one. Yeah. Okay, so let's say that this has a length of 0.3 meters. No. Yeah, that's vertical too. 0.0, this is 0.05 meters. And let's say that the mass of this thing is 2 kilograms. And we want to find the governing equation and the frequency. Okay, so let's draw a free body diagram at a general position. So we have this reaction force up here that isn't going to matter because that's our about point. And we have a weight force acting here that's equal to 19.62. About A, we have to calculate the mass moment of inertia. So this is the point A. So IA is equal to 1/12 times 2 times the quantity 0.3 squared plus 0.05 squared. That's for the center, but we need the parallel axis theorem part that's equal to 2 times the distance from the center of mass to A. So that's 0.15 squared. And so we calculate that. Okay, and that's kilogram meters squared. We could, you know, with any of these rigid body things, we could write out rho force moment, but in this one we might as well just do the trigonometry. So we have a length here of 0.15 meters and an angle of theta, and we want this horizontal distance because that's the moment arm. So that's equal to 0.15 times the sine of theta. And so rotational Newton's second law, the only thing producing a moment about A is the force of 19.62 times this moment arm, and that's a negative moment. And that's equal to 0.06042 times alpha. So we get alpha is equal to, could you tell me what, so 19.62 times 0.15 divided by 0.06042. So at alpha plus some constant, sorry, this is, no, alpha. Alpha plus some constant times sine of theta. 48.709 theta, nope, sine of is equal to 0. And rewrite that as theta double prime plus 48.709 sine theta is equal to 0. This approximately gives us theta double prime. So if we're dealing with small angles. Oh, really? Okay. So if you have small theta, we have theta double prime plus 48.709 theta is equal to 0. So that's our governing equation for small angles. This is the natural frequency. So that's our omega sub n. And so the frequency is 1 over 2 pi times 48.709. What do you get for that? .75 hertz. I don't know how many of you have seen demonstrations of pendulums, but I mean, in a way, it's as surprising as the fact that an oscillation of a mass on a spring has the same period of oscillation no matter how far you pull it back. Like that's a weird coincidence. And it's maybe even weirder with the pendulum because you think like, oh yeah, you pull it up 10 degrees, it takes like basically the exact same time for one oscillation as if you pull it back half a degree. But if you pull it, intuitively, if you pull it back half a degree, gravity is doing so little to make it move that it's just going so slowly the whole way. If you pull it back 10 degrees, gravity has a lot bigger lever arm to make it move quickly. I don't know. Mm-hmm. Of pendulums. Mm-hmm. Yeah. I hadn't thought of this before, but maybe I'll do a spreadsheet. Well, yeah, it won't take long. No, it doesn't. Do a spreadsheet where where I plot out what this theta as a function of time looks like if you have big angles and you have to use that sign, and you can compare what that looks like to the small angle approximation for different angles.